Good day, everyone. I hope that you're all enjoying your spring break. On the last couple of days in school before we started our spring break, we were dealing in class with what we call optimization problems. These are problems where you're trying to maximize a quantity or minimize a quantity. And on the last day before our spring break, I went through the beginnings of the solutions to two of what I called the more challenging problems that we've encountered so far. One of them involved maximizing the area of a particular window called a Norman window, and I'll be posting the complete solution to that within a day or so. The other one was this problem that we're looking at here. What you have is a 3 by 2 meter corridor that pedestrians are going to be able to walk through, and the wall is being painted, and we have a ladder which goes from the street below up to the wall. The question is, what is the length of the shortest ladder that's going to reach the wall? What we reasoned out is that the shortest ladder, not only does it have to touch the street, obviously, and it has to lean against the wall, the shortest ladder has to be one that just, quote, barely touches the top right corner of that corridor. We said in class that that becomes obvious because if you're going to claim that it doesn't touch the top right corner of that corridor, I think it's pretty clear that we can make a ladder that's even shorter than the one you're looking at here. And we can continue to make it shorter and shorter and shorter until it touches the top right corner. What we also said was that this ladder that you're looking at is not the only ladder that can meet those three conditions of touching the street, touching the wall, and just barely touching the top right corner of the corridor. For example, this green ladder will do the trick. And this blue ladder will do the trick. When we take a look at all three of these ladders, I think it's clear that the length of the ladder is different for each of these. And that kind of brings us to the main idea behind maximization problems or minimization problems. This is a minimization problem. What we have is something, I'm going to call the length of the ladder L. We have something which we would like to make as small as possible. And the basic idea behind doing this is if we can come up with a function for L in terms of one other variable, doesn't matter what that variable is, if you can come up with a function for L in terms of that variable, then the idea is if there's a minimum value of that function, that at that point, dl, the other variable, will be critical. And we haven't really run into too many situations where it's critical for any other reason than the derivative being 0. This is the whole idea behind what we're doing. There is going to be some value of this variable that is the ideal value of the variable that will produce the minimum length of the ladder. So the problem becomes, what is the function? We have to come up with a function for L in terms of one other variable. And by the way, even though I'm using a graph here to explain the ideas behind what's going on with optimization, we're not going to solve this graphically, we're going to solve it algebraically. Well, we need to introduce a variable. We need to introduce something that's going to be thought of as being plotted on the horizontal axis. And I'm choosing to put an x in here for the distance between the foot of the ladder and the corridor on the street, and a y for a variable as the distance between the top of the ladder where it meets the wall and the top of the corridor. And I know that in class I've probably said stay away from x and y, but I'm going to go with it anyway. I'm just going to arrange things when I do my math here so that my dependent variable, of course, has to be L because that's the thing to be optimized, but I'm going to arrange it so my independent variable is x. So again, what we're going to be looking at here is finding dl dx and leading to critical values of x, and that will lead to the minimum value for L. It doesn't matter what the graph looks like. We're never ever going to really look at the graph. So how do we begin here? How do we come up with a formula relating L and X? Well, unfortunately, we can't just dive right in and get L equals a function of x. But what we can do is use the Pythagorean theorem to at least get started. In this large triangle, and I believe we did this part in class. In this large triangle, the hypotenuse is the thing that we want to optimize. And the hypotenuse squared is equal to the sum of the squares of the other two sides. The base of this triangle is 2 plus x squared, plus the height of this triangle is 3 plus y squared. And here's the problem. We'll worry about the squared part on the L in a bit. As I said, we want a function for L in terms of x alone. We do not want y. So what we need is a secondary equation which will relate x and y. And the key idea here is for you to recognize that these two angles are equal. And assuming that everything is perpendicular to the street, and the street is level, and the corridor is all nice and square, what we've got are a couple of similar triangles. This triangle here is similar to this triangle here. Now, what does similarity mean? It means that all of the corresponding angles match. More specifically, if we want to get into the details here, this obviously is a right angle, this is a right angle. We don't even need to go any further. We can just recognize that if those two pink angles are the same and they are both in right angle triangles, then the tangent of either of those angles will be the same. If I take a look at the top triangle, the little green triangle, the tangent of that pink angle is opposite, which is y, over adjacent, which is 2. When I take a look at the other triangle, the one that I've got yellow lines on, the tangent is opposite, which is 3, over x, which is 2, which is adjacent. And there's the formula that we're going to use to eliminate y. When I rearrange this for y, x times y is equal to 6, which means y is equal to 6 over x. And that means that L squared is equal to 2 plus x, quantity squared plus 3 plus 6x to the negative 1 quantity squared. We talked in class about the fact that this equation here for L, which is now a function of x alone, can be differentiated, but you do not need to take the square root of both sides. We're just going to dive right in and differentiate this the way it is. And I'm going to come back to how this is helpful a little bit later. But don't worry about taking the square root of both sides. If I differentiate everything with respect to x, which is what I'm doing, I'm going to get 2L dl dx equals 2 times 2 plus x raised to the 1 plus 2 times 3 plus 6x to the negative 1 raised to the 1 times the derivative of what's inside. And I didn't have to worry about the derivative of what's inside, in other words, the chain rule here, because what's inside is 2 plus x and the derivative of 2 plus x is 1. So I didn't need to worry about that. However, when I wrap that 2 around the base of 3 plus 6x to the negative 1 and drop 1 from the exponent, I now have to multiply by the derivative of 3 plus 6x to the negative 1, which will be, well, the derivative of 3 is 0, and then the derivative of 6x to the negative 1 is negative 6x to the negative 2. And there is really not a lot you can do with this. I can factor out a 2 out of these two terms. Don't forget, when we're at this stage, we're talking about one term plus another term. So I can factor a 2 out of that. I'm inclined not to worry about it, but I will factor it out anyway. So I get 2L dl dx, and I just noticed, by the way, that when I factor that 2 out, it's going to cancel with the 2 on the other side, so this is actually a really good move. I have 2 plus x to the 1, and then I have plus, well, let's move that negative 6x to the negative 2 over here. So I have the negative 6x to the negative 2. And I have the 3 plus 6x to the negative 1 left over. You might be wondering why I'm not factoring out that negative exponent in the form of x to the negative 2. It's because I also have in there 6x to the negative 1. So my thinking is, let's just multiply out that whole thing. This whole thing. Let's just multiply this out and then worry about factoring out exponents. By the way, the 2's cancel. So what we're going to end up with here is L dl dx equals, I have 2 plus x, and then I have minus 6x to the negative 2, which I need to multiply by the 3 and by the 6x to the negative 1. So I'm going to get negative 18 x to the negative 2 and minus 36 x to the negative 3. I'm just going to step back and double check my math there. Negative 18 times x to the negative 2 is fine, and the other term is right as well. I guess I don't really need brackets around there. So now, what do you do with this? Well, we have negative exponents, so let's factor out the lowest exponent on the top, which would be x to the negative 3. And this is where things start to get a little bit weird, but it's all going to come together. I'm going to get 2x to the 3. I'm going to get x to the 4. So this is where you start to get a little apprehensive that now you're saying, well, I'm getting a degree 4 polynomial. That's okay. I'm going to have minus 18 x to the 1, and then I'm going to have minus 36 at the end. And this, of course, on the left-hand side, I have an L there. So rearranging now for dl dx, I get on the top x to the 4 plus 2x cubed minus 18x minus 36. And then on the bottom I have x to the 3, and part of me wants to just write L, but what I'm going to put in for L is going to be the square root of this. And I'm not going to worry about the fact that it has negative exponents in it. So I have the square root of that, which is 2 plus x squared plus 3 plus 6x to the negative 1 squared, all raised to the half. Just double checking, and it looks good. So now, what about our critical values? Well, we're going to eyeball the top. And we're going to ask ourselves, what values of x make the top 0? And I'm going to come back to that. When we look at the bottom, when I look at, for example, this factor, and I say, well, there's a critical value of x there of 0, I don't even need to consider the validity or the possibility that that's going to be a solution. Because if you look at your diagram, if x is 0, that means the ladder is standing straight up. And that means it doesn't meet one of those conditions, which is it won't touch the wall. So whatever that x equals 0 means, it doesn't have any meaning in terms of this problem. So we eliminate it. We can also look right now, everybody, at this whole thing being 0. So is there a value of x that makes this factor equal to 0? Well, you know what? I don't care if there is, because if that's equal to 0, since that's the length of the ladder would have 0 for a length, and that doesn't make any sense either. And in the end, what we discover is whatever critical value we would get for this bottom factor that's underlined in green, it gets tossed out as well. And what that means, everybody, is we're left with only the top equals 0. And it's not often that I do this. I normally say you do it by inspection, but we're going to actually write out x to the 4 plus 2x cubed minus 18x minus 36 and solve this polynomial equation. Now, you could attempt to solve this by going to your Math 30-1 factor theorem and synthetic division content that we've learned. But whenever you have a polynomial and there are 4 terms, you should always ask yourself if factoring by grouping works. Factoring by grouping is something you use in Math 10. We occasionally run into it in Math 20 and very rarely in Math 30. But it's one of those things that we need to keep track of because it does come in handy from time to time. We're going to group the first 2 terms together, and we're going to group the last pair together. Remember, this is equal to 0. I can, out of the first term pair, factor out x cubed and be left with x plus 2. The idea behind factoring by grouping now is that you want to see if you can factor something out of the second pair that leaves you with exactly the same thing you're left with when you factored the first pair. And if I factor negative 18 out, I'm left with x plus 2. And now what I can do is look at this term and this term, which are being subtracted, and say there's a common factor of x plus 2. And if I take x plus 2 out of the first term, I have x cubed, minus out of the second term, I have 18. So this is the factored form of the numerator of our derivative. What that means is x plus 2 can equal 0, or x cubed minus 18 can equal 0. Well, if x plus 2 equals 0, we're left with x equals negative 2. Well, that doesn't make any sense. X has to be a number greater than 0 when you look at your diagram, because that's how far the foot of the ladder is from the corridor. When we solve this second factor being equal to 0, we get x cubed equals 18. So x is equal to the cube root of 18. And this is a critical value. This was a critical value as well. Of all of these critical values that we've got, the x equals 0, which is to the left of the screen right now, the x equals whatever that would make this factor 0, the x equals negative 2, those are all critical values of x that are not in the domain of the function, at least not in terms of the real application of this, which has to be a length of a ladder. So the only critical value of x that makes sense is this, which means this is going to lead to the minimum length of the ladder. And if we want to find the minimum length of the ladder, we can go back up here to our formula for the length of the ladder. Put in the cube root of 18 for x, and run it through the calculator. I'm not going to write anything else down here. I'm just going to grab my calculator. I'm going to begin by taking the cube root of 18, which is 18 to the third, and I'm going to store it as a. So what's the length of the ladder? Well, I'm going to calculate what L squared is first by taking 2 plus a, quantity squared, plus in brackets 6 plus, pardon me, 3 plus 6 over a end bracket squared. And then I take the square root of that, and I get this for the answer to the problem. And I think, I seem to recall that when you take a look in the back of your textbook at this problem's answer, it just says about 7 meters. So that's the solution to that problem. Again, not that it really matters, everybody, but if you take a look at all of the work that we did here in this question, it's fairly extensive. If you knew how to differentiate functions that are trigonometric in nature, this would have taken us probably about a quarter of the amount of time and thought and workspace. And certainly in the next unit when we deal with trigonometric differentiation, I will show you the solution to this problem using trig, which is not nearly as scary as you think it might be. I hope that helps. As I said, in the next day or so, I'll post a solution to the Norman window problem. In the meantime, have a fantastic rest of your break. Take care.